Hello, brothers and sisters. My name is Mark Maeda. I'm the member of Group 6 that will be walking us through Lab number 2. My associates are Preston Hahn and Robert Nielsen. So we have a lot to cover, so we're just going to dive right in. So first thing, we were given this gigantic truth table here and instructed to derive the Boolean equation from the following truth table in SOP form, and then reduce it down, right down there. So went ahead and did that here and wrote it out in Word documents so you guys can read it nice. So first thing we notice here is that there is an even number of not A's and A's. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, and 5. So right away you're able to knock out all the A's, and then when you do that, there are an even number of all of these terms. So you're able to cut the equation in half. From there, you can cancel out the D and the not D, the C and the not C, the D and the not D, the B and the not B, and then we're left with not X equals not C or not B and not D, which as we go on, we will go ahead and prove elsewhere. Okay, so the next part of this, we're given instructions to plug it all into a KMap, which I've done right here. Now, real quick, I find it a lot easier to plug into KMap by first looking at the table and seeing which grouping, ones or zeros, has the fewest number of terms. In this case, we have 10 ones and 1, 2, 3, 4, 5, 6 zeros, which when mapped out look like this right here. And so it's a lot easier and a lot faster to go through and do the zeros first and then fill in the ones because it's always going to be a 1 or a 0 or an X, I suppose. So from here, we are able to loop terms together. As the book says, you can loop anything so long as it's a power of 2 and it's connected, or the four corners. So here we have one big block, 8 terms, that is 2 cubed, so that's a power of 8. And then we have the four corners. Now really quick, but just because I'm a nerd and I'm going to be real thorough about this, I want to discuss real quick why the four corners work. Now we know that K-tables work on gray code. And so the four corners here, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and 1, 0, 0, 0, all are right there. Those are the four corners. And as you know, a gray code is a code where only one bit changes at a time, making that possible to do. Somebody who had either no life or is a lot smarter than me figured that out. So anyway, we plug it all in. The software gives us the sets that we copy and paste into our answer, and then we also derive our equation from there. So as the book says, when we look at these, the loop numbers, if a term changes between the numbers in the block, we can drop it from the equation. So here we see in this main block of 8, both the A's and the B's change, and C changes from 0 to 1 between these two rows. So we're left with not C for our first part. And then for the four corners, a little bit trickier, but not bad. So we see here that A changes between the two, but it stays not B through the two columns. And then similarly, we see that it stays at not D, but C changes between the two. So we're left with not C or not B and not D, which, as luck would have it, is exactly what we found in our equation. So go us. So the next part of our assignment, or rather our lab, was to build the circuit using the 7400 library. So the first part looks like this. I'm not gonna go into super ton of detail here, but basically the 7400 gates are all, or rather the 7400 chips are all basically packs of gates. So you see here we have 6 inputs, and each one has an inverter on it. So the 7404 is just a hex inverter. So here we have D coming in and going out, going in 0 and coming out 1, so that's inverted. Similarly, the same thing happens for C and B. Next, we have the A. We know we need, I believe it's just 1A. Yeah, we just need 1A. So we have the B coming in, the A and the B both coming in and then coming out as the output there. So this output comes out over here into the 7432, which is this one. No, this one. Which is our OR gate. So we have that there. And so that's just how you build that. So as you see, we have our B or D coming in with our B, and then both these inputs are going into the AND gate, and the C coming in and then going out here to the OR gate, which matches our equation, not B and not D, or not C. Okay. Next thing we were asked to do was to, now this one was really cool. Build it with just a straight 70, the entire equation with just a straight 7400 chip, which is 4 NOT AND gates. Now, as you know, a NOT AND gate is a complete gate, which means that it can represent any values that we need it to do. So we have our inputs here. So as you know, two of the same input going into a NOT AND gate works the same as an inverter. So we have NOT B, NOT D. The outputs for those coming around here and then going into here to create another output there. So that's a NOT. And then the C that's coming in combining with the output from the NOT B and the NOT D and combining with the C to make that there for the correct output. Next, and I kind of feel like we should have covered this one first, but this is what it looks like on gate level without the 7400s. So we have the inverted, the double input NOT ANDs to create the inverters, then coming in for an and as we know from our theorems, an OR gate can also be rephrased as a NOT AND gate with inverted inputs. So we have the C gate here that doesn't have an inverter on it. Since we're looking for a NOT C, that works. And since this is a NOT AND gate, and we're looking for an AND gate, this also works. So this NOT AND gate essentially is functioning as an OR gate. The final part of our lab here was just kind of a write-up where we came up with the number of input gates, and pins, and that was a little bit tricky. It just kind of required a lot of critical thinking and a lot of counting, which to be full disclosure, I wasn't great at. But we got through it. And the moral of the story is that the 7400 SI chips are a really great way of simplifying our circuits, and also it pays a lot. It pays heavy dividends to properly simplify your Boolean equations before. Oh goodness, I have a countdown. Sweet. Hang on. Before you go into it pays dividends to simplify your equations before going into circuit building. Similarly, it also proves that how useful a tool KMaps can be when simplifying equations. All right, so that is Lab 2 in a nutshell. Again, I'm Mark Maeda, and have a great night.